All right, picture this. You're stationed on a massive drill ship right in the middle of the ocean, and suddenly, bam, a generator trips without warning. Just like that, a colossal amount of power vanishes. Now, on a system this incredibly complex, if a human operator had to react manually, it would literally take way too long. We're talking about a scenario where seconds, actually, scratch that, where milliseconds absolutely matter. You absolutely need a system that acts faster than humanly possible.
So, what actually happens when a massive 7,000 kilowatt generator suddenly just goes offline? Well, if left unmanaged, that sudden imbalance could cascade, pulling down the other generators and causing a complete ship-wide blackout. But instead, in a fraction of a second, this automated control layer steps right in. It instantly recalculates the load distribution across the remaining generators, rebalancing all that heavy lifting before an overload can even trigger. It happens so fast, honestly, you might only notice a tiny flicker on the monitors.
To really appreciate this, we gotta grasp the sheer scale of the power plant we're talking about here. In this explainer, we're looking at the GF 12,000 Drillship, which boasts a staggering 42 megawatt power plant. To put that into perspective, that is enough electricity to power a small to medium-sized town, and it's all being generated on a single ship floating in deep water. This massive output is driven by 6 enormous diesel engines, so coordinating them perfectly, it's absolutely critical.
Okay, let's dive into this and dissect this mechanical brain. We're going to cover its 4 core functions: auto-synchronizing the grid, the load-sharing logic, proactive start and stop, and fast blackout recovery.
Now, the system we're talking about here is called the Power Management System, or PMS. Formally, it's defined as the automated control layer governing generator synchronization, load sharing, load-dependent start and stop, and blackout recovery. But why does it exist? Well, because manually managing 6 massive generators in real time, especially during a sudden fault, is just far too slow and, frankly, way too error-prone. The PMS automates these critical responses at a speed and consistency that no human operator could ever match.
I absolutely love this analogy from our source material. Think of the PMS as an orchestra conductor. You've got 6 individual generators, those are our musicians, and each one is perfectly capable of playing its part alone. But to sound like one coordinated, flawless performance, you need a conductor, actively synchronizing their timing, their volume, and telling them exactly when to enter and exit. The PMS literally makes 6 massive generators play as one seamless, unified machine. And this brilliantly illustrates why software is just so essential here.
So, let's move to our first function, auto-synchronizing the grid.
Let's see how this builds, because achieving this requires some incredible precision. Before a standby generator can actually connect to the live power grid, the bus bar, it has to be perfectly aligned. The PMS automatically matches the starting generator's frequency, its voltage, and its phase to the running bus bar. And only when all 3 match perfectly does the PMS automatically close the breaker. If you didn't have this and you just slam the breaker closed, you'd get a massive disruptive electrical clash that could severely damage the equipment. It's really a delicate, highly automated dance.
Which brings us right to function number 2, the load-sharing logic.
Now, what's really interesting here is that once the generators are on the grid, the PMS faces this escalating challenge, balancing the massive electrical demand measured in active kilowatts across all the active generators. Now, symmetric sharing is kind of what you might expect. It's a straight 50-50 split, where each generator carries an equal proportional share. But think about it. If generators are of different sizes or capacities, a 50-50 split is exactly the wrong choice, right? It risks pushing a smaller unit way too close to its maximum limit, risking an overload. That is where asymmetric sharing comes in. It deliberately splits the load unevenly, basing it proportionally on each generator's actual capacity or condition, which keeps the whole shebang balanced and safe.
Moving on to function 3, proactive start and stop.
This function is essentially about predicting the future. It's there to optimize fuel use and engine wear, while ensuring you never get caught short on power. You see, the PMS constantly monitors the total demand against the available generating capacity. And there's a golden rule of thumb here. A good system acts on demand trends, not just alarm thresholds. So let's say it detects a rising demand trend. Maybe the active heave drawworks are working harder because of rougher seas. The PMS doesn't just sit around waiting for an overload alarm to sound. No way. It proactively starts an additional generator well ahead of the load spike, ensuring a super smooth load transfer instead of an unplanned, really messy trip.
And finally, we hit function 4, fast blackout recovery.
This is literally the absolute highest stakes scenario for any marine engineer, recovering from a dead ship and the total loss of the main power plant. When the lights go completely out, the clock is ticking. Let's walk through this timeline. In milliseconds, the PMS detects the blackout. Then, within seconds, it ensures emergency power is prioritized to keep life safety and critical navigation systems alive. Then, over the next few minutes, the pre-programmed generator restart sequence kicks in. So, rather than this chaotic scramble in the dark, the PMS restores full plant capacity step by step automatically. It brings generators back online and restores the load in a highly structured, super safe sequence.
So the crucial point we need to take away here is this. While this blackout recovery sequence is incredibly sophisticated and yes, it's pre-programmed to restore power automatically and prioritize critical systems, it is absolutely never a fire-and-forget system. Operators just cannot sit back and watch it happen. The system still requires human monitoring and manual confirmation at key steps. Why? To verify that whatever fault caused the blackout in the first place isn't going to just immediately trip the system again during the recovery.
You know, you simply cannot treat this automated recovery logic as entirely hands-off. Assuming the computer is just going to flawlessly fix a major cascading failure without human oversight, that risks absolute disaster on a drill ship. Human verification remains the ultimate failsafe. The PMS is there to handle the blinding speed and that incredibly complex coordination, but the human engineer, they're there to provide the critical judgment.
Which kind of leaves us with a fascinating paradox, right? We rely on this mechanical brain to manage 42 megawatts because it can think and react in milliseconds, way faster than we ever could. But if a machine can think in milliseconds, what happens when it makes a mistake at that exact same speed? It's a really delicate, high-stakes balance between brilliant automation and essential human oversight. And it for sure makes you wonder just how deep the safety systems on these incredibly complex drill ships really go.